du jour is, oh, I didn't mean to do that.
Well, I'm sure she's thought of it, but said no about Lindsay.
Go back. I didn't mean to do that. Wait,
Let's mute yourselves if you're not speaking, please. We're getting a little crosstalk.
okay.
How about that Robert guy?
I can't, my screen looks different. Okay, now,
From
why is that like that? Why is that not showing the whole screen?
We see your whole screen.
No, you're not. Now it's there.
Not what he's.
Okay. The mystery came up why there's no methylene blue. Now, I thought, this being a science group, in my ignorance, I thought that everybody took organic chemistry. And this would resonate with everybody. Now, this is Dick's world and my world, okay? I did not realize that in engineering, I did not know this, because I went to Penn, and Penn had a big chemical engineering program. Elon Musk went there, but he did electrical. And there were plenty of kids in my organic chemistry class from the engineering school.
From chemical engineering.
Chemical, I didn't, who knew? Who knew to ask? You knew, I didn't know to ask. And so there's a whole group of people who deal with electrons who never took organic chemistry, which I did not realize until now.
See,
So-
when I went to school, they didn't have carbon fiber for buildings, so I would never know anything about that.
Okay, why did I do that? So, why this is not behaving, I don't
It
know.
might be set to auto advance or something.
No, it isn't. There you go. Okay, so I thought I'd have to give you a little bit of organic chemistry terminology during the course of the lecture. But, you know, when I was young, my father, who was very smart, went to Harvard Law School, had no interest in science. I've said this before here, had no interest in science. But I was, and I would sometimes talk about scientific subjects. And he would look at me and say, "You are a compendium of useless information." And so I'm going to continue that tradition. If you have a blank piece of paper and you write down everything important that I say, you'll still have a blank piece of paper at the end of this talk. So let's just give you a little terminology. What we have is the methane, which is CH4. And then a methyl group is CH3, R being some other moiety, whether it's an atom or a molecule. And then if the carbon is bonded over here to two other moieties or a double bond, it's called methylene. That's the terminology that we have. So one I like to go back to is it's a very short progress line. Two French chemists with very French names, Jean-Baptiste Dumas, who was a big star in his day, and Péligot, who was no religious assistant, and then to Heinrich Caro. So we're going to go back
Wait a
to
minute, the first guy only lived 4 years?
no. Is that what I wrote? They didn't. Yeah. Oh, no, I'm sorry. Yeah, it's 4 years old.
He was a prodigy.
17 years.
Wow.
I don't know what, it's wrong. It's wrong. It's just, okay. So, thank you, Dick.
You're reading too fast.
Yeah, right. So we're going back to 1834 and what was going on then. And that is what they tried to determine the composition of methanol. Now we know now that the composition of methanol has a methyl group, CH3, and a hydroxyl, OH. And a hydroxyl group in organic chemistry makes something, an alcohol. So what we had was CH3OH. Now, to put that in context, the periodic table by Mendeleev wasn't presented until 1869. In 1894, there was no concept of what matter was made of. There was no, it just didn't know what it was. It wasn't earth, wind, fire, water, that thing. But they didn't know what it was. They were trying to figure out what it was. And one of the things Dumas did, he did a lot of very important things. He changed the estimated atomic weight of carbon from 12.2 to which was by Berzelius, a Swede, to 12.011. And in order to figure out the composition of things, you have to know their atomic weights. It's actually very important work. And to show how far ahead he was of his time, Stanislaw Cannizzaro, who was in his day one of the most important scientists of his day, and nobody knows who he is. In 1858, he gave a lecture, which was one of the most important lectures of science. And he had a course on how to measure three things. Not how to measure, how to measure accurately. Freezing point, colligative properties of matter, freezing point depression, boiling point elevation, and how to apply the 1806 Avogadro's theory, Avogadro's principle, which nobody understood. Nobody understood it. And when he gave his lecture first in 1858, people came out saying he took the sand from my eyes. I didn't understand it, how important Avogadro's work was. Up in that point, it was just ignored. Nobody understood it. And to tell you about the importance of freezing point or boiling point elevation, freezing point depression, for those who put Chem 1. Freezing point depression, if you put a solute into a solvent, it lowers the freezing point. So for example, by the number of moles you put in. So for example, we'll do it by weights. If you have a glass of water, and I'll make up the numbers, you put up a glass of water, you put 10 grams of glucose in it, it lowers the freezing point by 5 degrees. Well, if you take sucrose, which is disaccharide, and double the weight, you'd have to put in 20 grams, because the same number of moles to get the same freezing point depression. So then you know the relative molecular weights or relative atomic weights. And if you start with hydrogen, pretty soon you can ratchet up all the atomic weights. And that's what enabled Mendeleev to create the periodic table. And what he did with Cannizzaro, after Canizzaro's seminars and 2-week training program, was he took the atomic weights, and basically what he did is he wrote all the elements down. I think he had 63, and he wrote down all their atomic qualities, their chemical qualities. He played solitaire, and he just made rows. And lo and behold, they came down into rows that made sense. And everybody looked at he's from St. Petersburg, Russia, which was a backwater. And everybody gave him a little pat on the head and said, I think you'd do better by putting them in alphabetical order. And then, but from his periodic table, he then predicted the existence of scandium, germanium, and gallium. And lo and behold, within a few years, they were discovered. And his fame took off like Michael Jordan's fame or like one of those starships from Elon Musk, because he had shown that matter had predictable components. And that matter wasn't this random thing of mush or something. They didn't have any concept of the electron. That wasn't until J.J. Thomson, 1898, he had the cathode ray tube, it was shooting electrons, and there was no concept of the proton or neutron until the next century. But this was the seminal work, because at that point, everybody recognized matter had components, and they were predictable, and they were combined in different ways to make the elements. But that was 1869. We're back in 1834. Now, the origin of the word methyl, because I'm going to figure out what methanol was. Methy is alcoholic liquid or wine, referring to intoxicating properties, and highly is from timber. So methyl is alcoholic liquid from timber. Now, methanol was around since Egyptian times. It's used for preservation. But when you get it out of wood, you get all these resins and acids, and nobody ever drank it. And what's interesting is my guy, Robert Boyle, he's the pressure times volume. Robert Boyle was the first person to distill it in 1660, but it never went anywhere. He distilled it out. So what we have is the methanol that shows the structure there. Now we're going to get to the concept of the radical. The radical in 2025, as we all know, is an atom or molecule with an unmatched proton. It just has an extra electron, and they're very vicious, as is ozone. It's not stable, but it's a very vicious product, the nature of anything. And likewise, nitric oxide has an extra electron. And interestingly, bleach. Bleach is a salt, is sodium hypochlorite. And then the sodium hypochlorite, people often call the hypochlorite a radical, but it's not. It's matched by a proton with the sodium. And but that breaks down into free chlorine with a single electron, and that's what really does you in. And the same thing when you put chlorine in a swimming pool, the sunlight takes the chlorine, Cl2, and breaks it down into Cl with an extra electron. Fortunately, it's so irritating, people run away from it. You couldn't run away from World War I, but now people will not sit around when chlorine gases near them. Now forget everything I said. And a radical in 1834 Dick was starting out in chemistry. A radical in 1834 was completely different. What they noted was that certain groups of atoms seemed to behave as a single unchangeable unit, a substituent, through a series of reactions. And one was carbon with 2 hydrogens seemed to just persist. And they were called radicals, completely different word. So Peligot and Dumas, they did, now they have good atomic weights. They had carbon, had 12 grams for every 4 grams of hydrogen and 16 grams of oxygen. And they knew their atomic weights. So they thought that it had a methylene radical, by their term, bound to a water. So it was actually, of course, a methane here, bound to a hydroxyl, a methyl group bound to hydroxyl. But they thought it was this because they matched up. Here's your carbon, hydrogen, 4, hydrogen, 3, 4, and 1 oxygen. So it matched up. So they call it hydrate of methylene. And that's what they thought that it was. And it also became customary, if you had a methyl group, CH3, to refer it as methylene, because it was their concept of a radical, because the CH3 tended to persist through various reactions. Now, to give you a little organic chemistry nomenclature, maybe everybody knows this, here's benzene. Now, in organic chemistry, the hydrogens are understood so that you wouldn't write it like this with all the carbon bonds, and they just put a corner there means carbon, and here's the bond. Hydrogens are understood. So a benzene ring, by the nomenclature now, changes its name when it has a side chain to phenyl. And if it has 2 things bound to it, it's changed to phenylene. Two. Now, here's a thiazole ring. Now, this one's 5 carbons only because I happen to have a good graphic of it. Thio is the Greek word for divine fire incense, because sulfur, when it burns, it gives off a real smell. And then nitrogen was originally called azote. When Priestley discovered oxygen, basically it's 20% of the atmosphere, and nitrogen is 80% of the trace gases. He found that oxygen supported life, but he also found that nitrogen didn't. Zotos is the Greek word for life, and azote is without life. So it's called azote. Then when the trace gases were discovered, CO2 and hydrogen, they didn't support life either. So the name didn't make any sense. So it was changed. Now nitrogen is a precursor to niter, which is in gunpowder. It generates niter. So it's called nitrogen. That's how it got its name. But azote and its suffix azole continue in chemistry. So it's thiazole. So it's a thiazole ring that you learn in organic chemistry. So now getting to methylene blue. So now we have Heinrich Caro. Now I did talk about this in my other talk. Heinrich Caro was a chemist, and he worked on stains. And originally, when William Henry Perkin was an 18-year-old college student in England, and let's see, it's 1844 approximately, he had a spring project to synthesize quinine. The project failed. But what he did was he ended up with a substance that stained his glassware, it stained his hands, it stained his shirt, it stained his tie, and he couldn't get it off. This indigo type stain, he couldn't get it off. And he realized right then that he had found a stain that looked just like the indigo that came from the indigo plant, which was shipped from India around Africa. It was quite expensive. He could make it for almost nothing. And he actually right then recognized that he had, even though he was a student, he went into the indigo business and ultimately made his fortune making dyes. And here's the structure of indigo aniline, which was a byproduct of his failed experiment. Here's the benzene ring, but it's a phenyl because it has a side and has an amine here. So this is aniline. That's the dye he discovered. And then he hired Heinrich Caro to work out stains for calico. Calico is made of cotton. It stains well. And they were getting it from the American South. And so to stain calico. But then Heinrich Caro worked for him for a while. And then he went to work for BASF in Baden, Germany, which is Baden Aniline and Soda Factory. It still exists, BASF. And he constructed this molecule here. Now here you can see the aniline here, and you can see a 6-member thiazole ring. And here it is an aniline. And here the chromophores are always around the nitrogen. That's what gives it the color, the very blue color. Now you can see there's no CH2 in our current terminology for methylene. And so if we go back to the original, what he started out with, the starting molecule that Henry Caro started with was this one here. Now there's no methylene here either by our terminology, but if we use the old terminology, there's our old methylenes from the 1830 terminology. And now people, I think John Day complained about the name in organic chemistry. It's like these crazy long names, but they don't. N means something's attached to nitrogen. N means something attached to nitrogen. So there are two things attached to nitrogen. What are they? Dimethyl, methyl, methyl. Phenylene, here's their phenyl group, but it's two bonds, so it's phenylene. And here's the amine, here and here. Now the amine got its name from Jupiter Ammon, as you all know. When the Romans, they had Jupiter as their chief gods, the Greeks had Zeus. And the Romans and Egyptians together created a new god called Jupiter Ammon. They played fast and loose with the gods. And the Jupiter Ammon, and there was a temple built to Jupiter Ammon in Libya. And in that area, right near the temple, in the ground were crystals, white crystals. And the white crystals were in fact ammonium chloride. And so it was it's a salt of ammoniac after the temple to Ammon. And that's cell ammoniac. That's how the amine, that's the adjective of that, got its name. It's from the god Jupiter Ammon. So amine. I'm sure you all knew that, but I just thought to remind you. Okay, now we get to the Geneva Convention of 1892. This was a very, very important meeting. All the big wigs were there, all of them were there. And they worked out the nomenclature that Dick and I studied in organic chemistry. This is where it all began. So I began looking at this picture here, and I noticed, is that me? Was I there, or maybe my great-great-grandfather? I really didn't know. So then I got really interested in this diagram, and look what I found. You look carefully. Cannizzaro signed the picture. See that? So I said, oh, which one is he? Now I found out he was the co-chair. So he had to have a prominent seat. I'm not just saying this, as a co-chair. So where is he? So I went on just Google images. Could it be him? I didn't know. I wasn't convinced. So I got this other image here. Could that be him? I got these label Google images. I don't know. And so I put it through the chat bots, and they made a worse job than me. They could not get it. They couldn't get it at all. Okay, so I just don't know he was there. But I know for a fact that Mendeleev was at this meeting. He was an important figure, and he was an important figure at this meeting. So where's Mendeleev? So now Mendeleev was always pictured, even when he's young, with this wild beard and this wild hair. But you'll notice that everybody at this meeting was so important. Everyone got a trim, including Mendeleev. So I couldn't match him exactly. So I went through his pictures. And this is, maybe, is this guy? Maybe that's him, trimmed up, maybe. I couldn't tell. I matched everybody else. Nothing else came even close. So maybe that's Mendeleev there, but I'm just not sure. So let's go a little nomenclature here. What do we got here? Let's see. So methylene, as we know, is now defined as carbon with two other moieties. Here are the two valence electrons. Now, more importantly about Jean-Baptiste Dumas, who nobody seems to have heard of, me. Jöns Berzelius was a Swede, and he was the main proponent of how matter was formed into products, into different components. Electrochemical dualism, that a positive charge glommed onto a negative charge, and that's what held everything together. And that was electrical chemical dualism. Now, there are many experiments that are done that result in all these downstream things and all sorts of important things. Dumas did an experiment which was almost irrelevant in terms of its utility. Oh, but here, I'm sorry, I meant to show this Faraday thing. Here, looking at electrochemical dualism, there were anions that went to the negative charge went to a positive anode, and cations went to the cathode. And that's how matter was all put together, nothing else. So Dumas in the 1830s did this experiment. He chlorinated acetic acid, a minor experiment, and showed that a positive hydrogen could be replaced by a negative chlorine. Well, electrochemical dualism doesn't allow that. If you've replaced a positive charge with a negative charge, how could they hold together? So here you have acetic acid here with a methyl group here, and you have the trichloro here. Now, trichloroacetic acid is used maybe to burn off warts. I mean, it's not an important product, but this completely changed science because electrochemical dualism wasn't the answer. And this was the first step. They didn't know about electrons, but it was the first step in science to understand that the valence electrons. They had to explain how you could replace a positive charge with a negative charge. This is one of the most important experiments in science, and nobody ever heard of it. So here's the conclusion here. Here we started out with our initial product here, and oops, what did I do? Here's our old term for methyl radical. So here's our methylene to methylene blue. Current nomenclature is here. Now you will note over here is Vita blue. And there's no blue in Vita blue, but that's a whole other story.
But he's definitely a radical.
It's radical.
Yes.
So now the mystery is solved. They all know.
History. Jerry, there were a couple of things in the chat that Steve brought up, and sometimes you see what seems like the same chemicals arranged differently, like CH3 and H3C. I'm making it up. Okay. Why are they, this is chemistry 101, and I was absent that day.
Okay.
So why is it CH3 in one case and H3C in another
Well,
case?
because if you have a central molecule, a central atom, and the three things are bound to it,
Yeah.
Generally you put the central atom C, and then the three things that are bound to it.
Yeah.
It doesn't read strictly right to left or left to right.
Yeah.
It doesn't do that.
We in chemistry can read it both
Well, yeah,
ways.
you wouldn't
It
look
doesn't bother
twice.
us.
If you saw H3C, that you'd find odd.
We see it the same
But
way.
you see a lot of times, nobody even pays attention to it.
So in some ways, you're writing it in a way that
It's easy
reflects
to write.
the way you would draw the diagram. if you were doing
Yeah.
it.
Because in some of your slides, you had, I think it was TH3 in one case and H3C in another case, in the same slide.
Yeah.
And it was like, huh?
Yeah, right.
That-
Well, you use
that
that
had-
organic. You just get used to it.
That
Well,
had to do
also-
with representing the formula, the empirical formula versus the structural formula.
Yeah.
Versus preserving these so-called radicals.
That's right.
Yeah,
That's
so-
right. That's
so-
the
their
answer.
positions.
That's the answer.
Yeah, so
And
if he goes
relationships.
back to methylene, he'll have the CH3s over there. You'll see it H3C. It's what's bound to what. So he's talking about how the thing actually goes together. Helps you to see which atom binds to which other atom.
Right, so you don't just add up the Cs and the
Yeah,
H's.
exactly,
you
exactly. It
wanna-
helps you to see
the structure.
see what the structure is gonna be.
So I was waiting for some emergent context of the discussion on methylene blue, because I maybe had heard of methylene blue as a dye once or
Yes.
twice in my
Well,
life, but just
okay.
recently I've been hearing about it because it's showing up in these junk ads.
Yeah.
So could you give us some
Well,
context?
first of all,
attached?
when Caro, he was in Baden, Germany, and Paul Ehrlich, he was the father of immunology. He got wind of this staining up in Baden. He was in Berlin with Koch and all the other people. That's where all the scientists were. And he went up to visit Caro and got the methylene blue. Now this is 1860, brought it into medicine. The Graham stain wasn't until 1864, when Christian Graham took existing products, crystal violet and saffron and made the Graham stain. That didn't exist. So methylene blue, Paul Ehrlich brought it back to Berlin, and they began staining bacteria. They could now see them for the first time, and that's how diphtheria was really discovered, because you could see the bacteria in the diphtheritic membranes. And it wasn't the gram positive, gram negative had to wait another 4 or 5 years before they got to that distinction. So methylene blue was used all over the place. Methylene blue in medicine is hardly ever used now, real medicine, but one of the things, if you have a sinus tract, because there's nothing in the body is blue, if you have a sinus tract that seems to be draining, you put it in here and see if the blue comes out there. But it doesn't really, it isn't used very much anymore. It can, I think in G6PD, you can use it to reverse some of the changes in G6PD.
Another thing that's going on here is that methylene blue is only one of the blues. There were a number of dyes that came out of this, and they were
Yeah.
different colors. They had that same basic structure, but they had different colors. And it's used tremendously in the chemical dyeing industry. There still is used.
But in the
Just slight
2020s,
changes.
we're hearing about some spectacularly fantastic properties that this has with respect to the mitochondria and
Yeah, you can stain it better.
energy production and stuff like that. It's some miracle cure for everything that ails you or something.
Well, there are quacks and there are charlatans. Okay, and the difference is a charlatan.
One looks like a duck and the other doesn't.
A charlatan knows what they're saying is false. They know it's false. And when they get discovered, they just go on to something else that's false. A quack believes the craziness. And they persist. And so when you have somebody like Robert Kennedy, he's not a charlatan, he's a quack. He believes it.
I think I've heard his name associated with this methylene blue BS that we're talking about.
No doubt,
So-
but he's a quack.
Well, it can have pharmaceutical
It does have,
effects.
so it does have some.
And that's what that's why he's promoting
if
it,
you-
because it will have positive pharmaceutical effects under certain circumstances.
That's right. You gotta be able to tell the blue pills from the green pills.
Beyond that,
Derivative of coal tar, isn't it?
Coal tar and potash. Potash is you take wood tailings and boil them, and the animal comes out with the calcium and potassium hydroxide, and iron comes out of potash. I mean, indigo comes out of coal as well.
Sodium hydroxide is very aging.
Oh, that's very, potash was really to get calcium and potassium hydroxide, but aniline is a byproduct of that too.
And so, they use that